Okay, question number 2 is there was a mistake in the answer. Yeah, I had erroneously marked it as D, but the correct answer is C. So, uh, so this is false. Okay, 1 comma 2 is a subset, so it does not belong. So it's a subset of n. So that's why this is wrong.
Yes, sir, I had that doubt only.
Yeah. And which question?
Question number 8.
Eighth question. Okay, so I saw the result and most of you guys had this 8th question wrong or you guys had left it. So let us discuss this. So SI is I plus 1 and so on for all I belonging to L. So let me copy this thing. This is the question, and C is a set, and the set is defined as starting from the ith number. So S1 is 1 to infinity, S2 is 2 to infinity, and so on. So that's how it goes. Okay. Okay. So S1 would be the set 1, 2, 3, 4, and so on. S2 would be the set 2, 3, 4, 5, and so on. S3 would be the set 3, 4, 5, and so on. So that's how these sets have been generated. Now, union of all these sets is natural numbers, which is true. If you take the union of all these sets, obviously S1 is the largest set, everything else is a subset of S1. So you basically have the relation S1 is a superset of S2, which is a superset of S3, and so on. So if you take union of all these sets, it will be just the largest set, which is basically the set of natural numbers. Right, so this is correct. Now, notice the difference between option A and B is this part. Here you have infinity, here you have n. So while this is an infinite union, this is the union of all such sets. B part is this union till some set Sn, which is going to be numbers n, n plus 1, and so on. Okay, so B part is just union of these sets. Now, obviously, for these sets also, the largest set is S1, which is containing all the sets, and this set S1 is just going to be the set of natural numbers. So this is also correct. Now, when you take intersection of all these sets, right? So if you take intersection of all these sets, C part, so that is, I'm finding an element which is common to all these sets. So there is going to be no number, there exists no natural number such that n belongs to infinite intersection of SI sets. So this is what I can prove. Okay, you can actually prove this thing. So how do I prove this thing? So I can prove this thing by saying that take any n. Take any n belonging to natural numbers. And so n is not contained in Sn plus 1. So Sn plus 1 starts from the number n plus 1. So Sn plus 1 will not be containing the number n, but Sn plus 1 is a part of the intersection Si I equals to 1 silicate. So for any n, you can take n as large as possible. So you can think n as 1 million. So I'll say that 1 million and one set onwards on the sets, they won't contain the number n. So intersection will not contain 1 million. Similarly, the same argument holds for 1 billion or any number larger than that. So the basic idea is that the intersection set is going to be a null set because there is going to be no number which is contained in every set. So this thing is true. Now D option is intersection Si is null set for any n. So now this is a finite intersection. Okay, so the difference with a finite intersection is that you could have, let's say, the intersection of first 100 sets, or you could have the intersection of first 200 sets, or so on, or intersection of first million sets. So when you take that intersection, so I will have the number n plus 1 always contained in the the finite intersection of n sets. So you can prove this. You can prove this. Okay, so for every such set, n plus 1 will be a member. Right? Every such set is going to contain n plus 1 number. Okay, so n plus 1 is always going to be contained. Similarly, n plus 2 is always going to be contained, and so on. So a finite intersection of these sets will not be a null set. It will have numbers greater than n plus 1, greater than equals to n plus 1 contained. So all numbers greater than equals to n plus 1 will be this set. So basically, the intersection. Okay, so basically the finite intersection Si from I equals to 1 se leke capital N, this is nothing but the set Sn. Because like I told you, the sequence is S1 contains S2, which contains S3, which contains S4, and so on. It is going to contain set N minus 1, which is going to contain set N, and so on. So the finite intersection of these sets is going to be capital N. And if you have got this question wrong, I'll tell you, I analyzed your results and all of you either left it or you got this wrong. So if so don't feel bad about missing out on this question. And the more important thing is asking doubts if you still don't get it. Okay, so I want you to be perfectly confident with your doubts, because a lot of times what happens is you feel that others are going to judge you if you don't ask doubts. I don't want that. Okay, I want you to ask me doubts if you still don't understand this.
So in this question, the third and the fourth both are false, right?
No, third is true. The third is true. So see this proof. I prove here that no natural number can be, and no natural number is contained in intersection Si, infinite intersection Si. Why don't you give me a natural number, large natural number that you can think of? Give me any large number.
Like, if not large, if we'll take it, oh yeah, that's still infinity. But if we are taking the intersection till infinity, then it will contain all the numbers, like from the
No,
first set only. So
the union will
not
contain
the
all the
first set.
numbers. The union
Yeah,
contains all the
it's
numbers.
intersection.
What is intersection? Intersection is, so let me construct a Venn diagram, all right? So what's happening is set S1 is, suppose this square represents the set of natural numbers. So the set S1 is this entire box, okay? Now set S2 does not contain one number, that is number 1. So this is the set S1, sorry, S2. Then set S3 will be smaller. Set S4 will be smaller. S5 will be even smaller, and so on. So you see, you're collapsing the sets. The sets are sort of collapsing on each other. And when you do this for infinity, you'll be basically left with nothing. That's the idea.
Yeah, got it.
Okay.
And
So
if
these
we'll do it
concepts,
for, and the
these
fourth one, is it true or
uh,
false? Like I'm confused.
fourth is false, and that's why it's the correct answer.
Okay. Okay,
Fourth is
got it.
false. Okay, so if I talk about true, false, this is true, this is true, this is true, and this is false. And the question asked you a false statement. So that's why this is correct answer, which is basically because this is false. Uh, okay, so the fourth is basically a finite intersection, whereas third is an infinite intersection. Now, infinity is a concept which is very abstract to you right now. And today we are going to look at one more topic which is going to blow your minds even further, and that is cardinality. So I'll talk about it when we reach there. But you see, the idea is that these sets, they sort of, it's the idea is very uh, discomforting that the intersection of these sets should be null set, like nothing is contained in these sets. Okay, so the way to build a proof for that is always that you begin a proof with contradiction. Okay, so if you want to prove that the infinite intersection of sets Si is a null set, then start with assume some n natural number belongs to intersection Si, the infinite intersection Si, 1 to infinity. Okay, and then you show that it is not possible, so you arrive at a contradiction. So remember the first class we talked about types of proofs, and we did proofs using contradiction. So this will be one such proof wherein you find a contradiction. Okay, any other doubts apart from questions 2 and 8?
Yes, sir. Could you please explain question 3?
All right, question 3 is another very good question. This is one of those questions, again, many of you made a mistake. So this is a question wherein if you are attempting it with half mind, or you're not at your complete focus, you're not giving all your abilities to it, you're poised to make a mistake. So the question is that A and B are sets of natural numbers, and the question is can be true. So there's a difference between can be true and is true. Okay, so the question asks which of the following can be true. Now it's saying that both A set A minus B and B minus A are null sets. So when A is equals to B, then obviously this is okay. When A is equals to B, then obviously this is true. Because then what happens is set A minus B is equals to null set, right? So this is a situation where both the sets are same. Okay, so this is your set A and this itself is your set B. So both sets are same. So A minus B is, you subtract all elements of B from A and you get a null set. So option, and B minus A by similar logic will also be null set. So option A is true. Okay. Now the question is A intersection B. Now obviously if you draw it like this, suppose suppose you draw sets A and B in this manner. Suppose you draw this as set A and this as set B. Then what you get is that A intersection B is 5. Okay, so in this case, you have A intersection B as null set. So A set minus B. So in this case, what happens is A set minus B is equal to A, right? And B set minus A will be equal to B. So in this case, both the set minuses are giving the same set. So in this case, I'm not getting these are null set. But this is not necessarily true if this is the case. Now you could have a very extreme case where both A and B are null sets. So this was the catch here, and that's why I will call this as the most difficult question in this one, because you have to allow for this property from this chance. So question 3 was, according to me, the most difficult because you have to think that okay, there's this possibility that A and B are both null sets, and then what happens is that A intersection B also becomes null set. So A intersection B is null set, and in this case, what you get is A set minus B is also equal to null set, and B set minus A is also equal to null set. So this is the can be true kind of thing. Now, had this question been which of the following is true, right? Then only option A would have been correct. But because this question is can be true, option B becomes correct. Okay, so I played a little trick with your mind. So I wanted you to make this mistake, and most of you did. Uh, but then that is on me. Okay, that's my me being a bad examiner who's making traps to trap. But generally, our exams are not that bad. Okay, they are not going to make such traps. If such a question comes in the exam of DSC or ISI, this thing is going to be is true, will not be can be true. This is just sinister examiners like me who are making you fall. Okay, but this is learning process. Okay, I want you to pay extra attention to questions. That is what we are learning through these problems. All right. Uh, any other? I hope this one is clear.
Yes, sir.
Any other doubt? All right. So let us move to. I take the problems later. I want to complete set theory first. So let us do that. I hope you guys have started the past years because there are a lot of past years from this particular topic. So we talked about index collection of sets and everything. So this is done. We had to do relations. Okay. Now, relations are basically all sorts of connections between two sets which you can build. Okay, so we talked about functions. Okay, but functions had some properties. So functions are defined from some set x to some set y. So it is basically that every element in x is going to have an image, and this image is going to be unique. So you could have situations like this. What you cannot have is situations like this. And what you cannot have is situation like this, like something in X does not have an output. So every input has an unique output. Now it is possible that two inputs give the same output. That is valid. That is not a problem. But one input giving two outputs is not allowed. So that is the definition of functions. But I'm interested in now looking at relation. So relation is any arbitrary connection. You can have elements in X which are not connected. You can have elements in X which are giving to output. So everything is a relationship. All right. So in this class of relationships, so in class of all possible relationships, there's a class which is basically binary relations. Okay, so what are binary relations? So binary relations on set X and Y is a definite relation between elements of X and element of Y. Okay, so there's some sort of a relationship between elements of X and elements of Y, which we call as binary relations. So binary relationships basically take two elements and they check if this relationship is true or not. So for example, X could be the set of X is, let's say, the set of students, and Y is, let's say, the set of books that they have read. Okay, so this relationship, what it means is, let's say there's some student Amar and there are a bunch of books, let's say LOTR trilogy, and there's Godfather trilogy, there is what is that, werewolf and vampire thing, Twilight trilogy, there is the Shiva trilogy. So these are some different trilogies or books which are available in the library. So now let's say Amar has read Godfather trilogy and Twilight trilogy. So if I find a relationship R here, okay, then Amar R Godfather is true. What this means is Amar, our grandfather, being true means what? That Amar has read. This is the reading a trial relationship. Or so Amar has read grandfather. And when I write Amar or LOTR is false, it basically implies that Amar has not read LOTR. Okay? So I can only compare two things at a time. So this reading relationship is a binary relationship. It takes one element from X, one element from Y, it brings them together and sees has Amar read this book or not. If he has, then the relationship is true. If he hasn't, then the relationship is false. So it's as simple as that. Okay. So suppose I uh, I want to look at an example from the world of mathematics. So such a binary relationship between is the greater than sign. So greater than sign defined from the set of real numbers to the set of real numbers. So I take the set of real numbers R and R. I take a number here, small r1. I take a number here, small r2. So if R1 is greater than R2, then I write R1 greater than R2. If R1 is not greater than R2, then I don't write it. Okay, or I say that R1 greater than R2 is false. R1 greater than R2 is a binary relationship. Okay. Now, in the first class in microeconomics, we talked about swiggle, that is our preference relations. So preference relations basically helped us compare different bundles. So suppose there are goods X and Y, and there's this bundle A, which is, let's say, 3 units of X and 1 unit of Y. And there's this bundle B, which is, let's say, 2 units of X and 2 units of Y. Now, what the swiggle does is it takes two things and it checks if this relationship was true or not. Right? So if it tells me that A swiggle B, it means that A is weakly preferred to B. Okay. And if it tells me that A swiggle B is false, that is does not give me this output, it means that this thing is not true. Okay. So so suppose it tells me that this thing is true and B swiggle A is also true. So both these things simultaneously true, it would mean what? What does this mean? If A swiggle B is also true and B swiggle A is also true. So from your knowledge in consumer theory, what can you say about bundles A and B if both these statements are true?
So the consumer is indifferent between the two bundles, A
Very
and
good.
B.
So A and B are indifferent. Okay. On the other hand, if this thing were false and this thing were true, then what would happen? What would happen if statement 1 is true, but statement 2 is false? Somebody has to say. Come on, give me an answer. Give me a wrong answer for all you care. I mean, let us take this discussion forward. Why are you afraid?
So A is weakly preferred to B.
No, in this case, I'll have A strictly preferred. Okay, because A strictly preferred to B, when it is true, then this thing is true, but B weakly preferred to A is false. So only in this case, I will have this true and this false. Okay, if A were weakly preferred to B, then I cannot say for sure. Okay, so the idea is that I have to give one of these answers. I have to give either A preferred to B, A different to B, or B preferred to A. One of these three things has to be. Okay, so that is basically the completeness property that one of these three things has to be. Uh, so if this is true and this is false, then it automatically means that that A has to be strictly preferred, because only in that case you'll get this true and this false. Okay, so this is how we can get like if we get we can go from relationships to some sort of an understanding on preferences. But obviously, like I told you, for reasons about usability, preferences are not very good with to work with. So we try to convert them into utility functions, and that is the entire consumer thing. So I will not delve much into this relationship bit because that is not in our syllabus. I just like to talk about it because we have preferences and they are binary relations. So I want you guys to know what are relationships. But beyond that, as far as the scope of the exam is concerned, it is not something we need to worry about. Okay, so you can also graph relationships. So graph of a relationship is basically all the points x, y, so that x are y is true. Okay, so so if I ask you to plot y x y equals to 1. Okay, so xy equal to 1 is not sorry, suppose I ask you to plot x square plus y square equals to 1. Okay, so x square plus y square equals to 1 is the equation of a circle, right? So it's a circle with a unit radius and centered on the origin. Okay, so this thing is not a function. This thing is not a function because for any value of x, I am getting two different values of y. But you can classify it as a relationship. Now, in common parlance, when you're talking to your friends or your teacher, even if you call this as a function, nobody's going to beat you with a stick. Why do you call this a function? This is not a function. Okay, in common parlance, you can call this a function, but if you were to write a textbook or any let's say a research paper, then this is not technically a function. Okay, so this is a relationship. So you might see this word relationship being used for representing this, or you can call it a graph. The graph x square plus y square equals to 1. So the graph is basically defined as all points x and y such that this relationship is true. So the graph of this circle will be basically all points x comma y belonging to R square such that x square plus y square is equal to 2. So that is the graph. Okay, so that's all about relationships, and mostly we will never hear about them again after this class. You can very well forget it if you want. We move to the next topic, that is countable and uncountable sets. Now, so countable and uncountable sets is a topic which will be very new. So most of these topics, other than that, what we have studied till now, you might have read this in your 12th standard. This is the new thing that we are. Suppose I am measuring the size of two sets. So I want to basically compare the size of two sets. So suppose you go to your friend's house and you get a peek into her wardrobe and you see that there are a lot of shoes. She loves shoes. She has a lot of shoes. She has shoes of all colors, all types, everything. You get jealous. You automatically compare it mentally with the set of shoes that you have back at home, and you realize that you have a fraction of shoes that your friend has. So what you did is you basically saw the set of shoes that your friend has, and you compare the number of elements in this set with the number of elements, that is the shoes that you have in your world. And you realize that this set of your friend's number of shoes is way larger. Okay. So that's a mental comparison of two sets. Okay. So here we want to be able to generally compare the size of different sets. Now, first look at a few definitions. So the set phi is the empty set. It has no elements, zero elements in it. Okay. Now the set n of natural numbers. If n belonging to n, a set S is said to have n elements if there exists a bijection from the set 1 to n onto S. So we say that a set S, any set S has n elements. What does it mean? So suppose S is the set of shoes of your friends, and this pairs of shoes, and we say that this has n elements in it. It means n could be, let's say, 10, any number, 10 elements. So let's say your friend has 10 shoes. Okay, maybe you're not, you don't think 10 is a large number. I don't know. I'm saying take any number, 10 elements. So S has 10 elements. So what does it mean for a set to have 10 elements? The meaning is, so suppose the elements in the set S is, let's say, shoe 1, shoe 2, shoe 3, shoe 4, shoe 5, shoe 6, shoe 7, shoe 8, shoe 9, and shoe 10. So these are the 10 elements in the set of pairs of shoes that your friend has. What this means is that you can construct a bijection. A bijection is basically a one-to-one and onto set, right? Onto function, one-to-one and onto function. So you can construct a bijection from the set 1 to 10. So you can have a set 1, 2, 3, 4, and so on till 10. And then you can have a set S1, S2, S3, and so on till S10. You can construct a bijection between these two sets. You can construct a one-to-one and onto function from these two sets. So this set is basically the set 1 to 10. So if you can construct a bijection from this set to the set of shoes, then we say that the set of shoes has 10 elements. Now, obviously, anybody who does not even know bijection can say that this set has 10 elements. But when we are defining, we have to go into these nitty-gritties and go into details and defining it in the most correct manner possible. So that's why we have such a cumbersome definition of a set with 10 elements. But with time, you'll realize why do we have such a cumbersome explanation for this thing. Now, in this case, we say that these two sets have the same cardinality. The set 1 to 10 and the set of shoes has the same size or cardinality. So I'll come to cardinality in a bit. So a set S is said to be finite if it is either empty or has a finite number of elements in it. So a finite set is something which has no elements, or it has a finite number of elements in it. So you can construct a bijection from this set to that set. Okay. Now, suppose your one of your friend has a set of trousers, and in this set of trousers, he has a black trouser, a red trouser, a green trouser, and a white trouser. Okay, and he has a set of shirts in it. So in this set of shirts, he has a yellow shirt, he has a blue shirt, he has a brown shirt, and he has red is gone, pink shirt. Okay, so now these two sets have the same cardinality. Now I know that this has 4 elements in it and this has 4 elements, right? So they have the same size to them. So this has 4 elements, this has 4 elements. Now they have the same size. I'll come back to this example to also give a better idea of cardinality. All right, so both these sets are finite also because their size is 4. They have a finite number of elements. Now a set is said to be infinite if it is not finite, right? So if it has infinite numbers in it, then it is going to be an infinite set. Okay, so basically I have 3 types of set right now. I have the null set, the finite set, the finite but greater than null set, and the infinite set. So these are the 3 types of sets that I'll generally have always. Now what is cardinality? Now we refer to the size of a set as measured by one-to-one correspondences as its cardinality. So the size of a set is going to be called cardinality. Now if you use a different word than size and y, it will become clear in a bit. Now, two sets x and y have equal cardinality written as x is equivalent to y. Okay, so x double tilde y, so equivalent to y. Now, if there is one-to-one onto map x to y, then the cardinality of x is less than or equal to cardinality of. So this is an important. So this is the set of trousers and this is the set of shorts. So if you could construct a one-to-one onto map from this set to this set, then these two sets will have the same cardinality. And you can construct a one-to-one map like this. You can connect all these dots like this. And then you will say that the set of shirts and the set of trousers has the same cardinality. But if you were to, let's say, find one more trouser or lose one more shirt or something like that happens, then these two sets become of different cardinality. Their sizes become different. Okay. So this next thing says that if there is a one-to-one onto map from x to y, then x is less than or equal to y. So suppose this is some set x which has some elements in it, and this is some set y which has some elements. Now suppose you were able to construct a one-to-one and onto map from here to here. This is one-to-one onto map cardinality. Okay. So yeah, so when you have a one-to-one and onto map, suppose you have a mapping F, which is both one-to-one, which is basically a bijection, then you know that the number of elements here has to be exactly equal to the number of elements here. Now, I don't care if the number of elements, what is the number of elements, 10 or 100 or 1000 or billion, I don't care. If there is a bijection possible from one of the sets to the other sets, then the number of elements here has to be equal to number of elements. So suppose you are distributing chocolates. Okay, so y is the set of chocolates that you have, and x is the set of students in your class. Now you start distributing chocolates, one chocolate to everybody, right? So if you give one chocolate to everybody, and in the end, the last student gets the last chocolate. So you know for a fact that the number of chocolates has to be equal to number of students. So you construct a one-to-one onto map in this manner. Every student gets one chocolate, right? So it's a one-to-one onto map. And in the end, none of the chocolates remain. So, so you know that the number of students has to be equal to number of chocolates. But if there is a one-to-one map, if you give it, if f were one-to-one but not necessarily onto, then what happens is there are a few chocolates which remain after this. So you distribute every student one chocolate, so it was one-to-one, but the chocolates don't end. Okay, so chocolates don't end. So what happens is that some chocolates are remaining. So in this case, what you know for fact is that the number of chocolates must be greater than or equal to number of students. Okay, I don't know if chocolates remain or not. I just said that everybody got one chocolate. I have just this information that everybody got one chocolate. I do not know if chocolates were remaining or not. So then what happens is either the number of chocolates should be equal to or it should be greater than number of students. So in this case, this set of chocolates has to be larger in size than set of students. So we say that the set of chocolates is greater than or equal to the set of students. So this is how we like. Okay, so this is when you distribute chocolates and everybody gets one chocolate, but you don't know if chocolates are remaining or not. So in that case, you give a relationship like this. Okay. Now, so this is cardinality. So you define cardinality as some sort of preference rating on sets. So you give this thing if the set C is larger than or equal to set S. You give this rating if both the sets are of similar size. That is, you can construct a one-to-one and one-to-one. Now, if x is equal to y and y is equal to z, then x should be equal to z. So this is basically a transitivity of sorts on cardinality. So what this property is saying is, suppose you have a set x and you have a set y and you have a set z. And what you know for fact is that x has same size as y, which implies that there is a one-to-one onto map here, f. And y has the same size as z. So this is a one-to-one onto map G. Okay. So f is a bijection, G is a bijection. Right. So then what this property says that then you should also have x as the same size as z, which implies that there exists a bijection h going from x to z. And this bijection h going from x to z, so you can construct one of these bijections very easily. This bijection h is basically just g of f. Right, so suppose there's some element small x1 here, small y1 here, and small z1 here. So I'm trying to find a function which is one-to-one onto going from x1 to z1. So this is going to be my function h. So the function f can take x1 to y1 and the function g can take y1 to z1. So doing the operation g after doing the operation f will take this function x from y and then on to z. So at least one such bijection exists. Now I do not need to find multiple bijections here. Even if I can find one bijection, that is sufficient. Okay. So let us do an example for this. So let us take a set X, which is 1, 2, 3, just the numbers 1, 2, 3. Y, which is the set 101, 102, and 103. And Z, which is the set 202, 204, and 206. Right. So X and Y have the same cardinality. Implies there exists a bijection f going from x to y. Can you construct a function, a one-to-one onto function, which takes elements from this set to this set? Can you construct a function y equals to f of x such that this function is one-to-one onto on this domain and codomain?
Y is equal to 100 plus x.
Yes, very good. So y equals to x plus 100. So 100 plus 1 will give 101, 100 plus 2 gives 102, 100 plus 3 gives 103. Okay. Now, it's not necessary that there will be only one bijection. What I want you to appreciate the fact is that you can construct multiple bijections. I can construct another function f1. Okay, this another function f1 will be equal to, let's say, it could be, it could just be this numbering that f1 of 1 is 102, is 103. f1 of 2 is 102 and f1 of 1 is 100 and sorry, f1 of 3 is 101. So it need not have a formula, but it is defined in this manner. So this function will basically look like this, and this. So it's not necessary that there is only one bijection which takes you from x to y. Okay, if x and y are indeed of the same size, then it is possible to construct multiple bijections going from one set to another set. All right, so it is possible to construct multiple bijections here. Now I'm saying that y is also equivalent to z. Right, y is also equivalent to z. So can you construct a bijection from Y to Z? Let me ask this question to who do I see? Yeah, Yuvakshi. Yuvakshi, can you construct a one-to-one onto function going from set Y to set Z?
So Z equals to 2y.
Very good. So Z equals to 2y is one such function. Okay, so you can construct this one-to-one onto function. Now, finally, because x is equals to y and y is equals to z, I should also have x equals to z. I should also have x having the same cardinality as z. So I want to be able to construct a one-to-one onto mapping from here. So one such mapping was given to be my Kritika, I think, y equals to x plus 100. The second was given by z equals to 2y. So I can construct this one-to-one mapping as z equals to 2 times x plus 100. 2 times y, z equals to 2y, and y is basically x plus 100. So 2 times x plus 100. So this is just z equals to g of f of, sorry, f of g of, no, sorry, g of f of y, right? So that is your composition function going from one thing to the other. So you can construct a one-to-one onto map going from x to z, right? So this going from x to z is a completely plausible one-to-one onto map. Okay, so let's look at this Schroder Bernstein theorem. So this says that if x and y are set such that there are one-to-one maps fx to y and gy to z, then there's a one-to-one onto map h from x to, okay, this should be x to z. So x to y, you have some bijection, y to z, you have some bijection. So x to z also you have some bijection. Okay. So this is the Schroder Bernstein theorem, which basically says that the idea is that if you have equated the sizes of these two sets as equal and equated the size of these two sets are equal, then the sizes of these two sets are also rendered. That is the Schroder Bernstein. Now let us look at infinite sets. So first let us define what are infinite sets. So a set X is finite if it is either empty or has some finite number of elements in it. So I've already seen what's a finite set. Now a set is called countably infinite if it has the same size as n. Okay, so if a set has the same size as the set of natural numbers, then we call it countably infinite. This term is important, countably infinite. Yeah. A set is called infinite if it is not finite. I saw this already. Now, a set is called countable if it is, a set is called countable if it is either finite, finite is this definition, or it is countably infinite, which is this definition. Okay. And it is called uncountable if it is not. So basically the sizes of sets are arranged in this manner. To be jumping the gun, if you were to go in a mall of sets and look at sets being arranged in sizes, the size will come in this manner. There's the null set, then there's which has basically size 0. Then size 1. Size 1 will be singleton sets like element 1, element 2, element 3, and so on. So these are all sets of size 2, size 1. Then size 2. So this will be sets like 1, 2 is present, 1, 3 is present, then 1, 4 is present, 2 and 3 is present, and so on. So these are all sets of size 2. Then you talk about sets of size 3, 4, 5, and so on. So these are all finite sets. Then comes the size of first infinite set. That is the sets which have the same size as natural numbers. So it's going to be sets like natural number itself. The set n is basically the number 1, 2, 3, and so on. This has the same size as natural. But there are a bunch of other sets which will have this same size. Okay. So the smallest size is null set. The next available size is finite set. The next available size is the size of natural numbers. Okay. So we are going to look at a few sets which are going to have the size of natural numbers, and then we'll talk about uncountable sets. So the first example is the set of squares. So herein came the interesting thing. So consider the set N, which is basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and so on. And consider a set of perfect squares, which is 1, 4, 9, 16, and so on. Now, obviously, the set of squares is a perfect subset of set of natural numbers because all the numbers here, they appear here. Right? All the numbers here, they appear here. There is no number which is in the set N but not present in the set S. So obviously, the set S is a subset of the set of natural numbers. So herein came the interesting debate which happened, which raged, that which of these sets is larger. Now, the obvious thing is that the set N is larger because it's perfectly containing set S. But then the confusing thing is that these are both infinites. How do you say that one infinity is greater than the other infinity? How do you compare the size of two infinities? That became the problem. Okay, so that you cannot compare infinities like you're comparing finite sets. So therein came this whole idea that if you can construct a one-to-one onto relationship from this set to this set, if there exists a bijection f going from S to N or vice versa or N to S, whatever, then essentially S and N should be of the same size. Okay, so this was the revolutionary idea which came along, that if you could construct a one-to-one onto map from one set to the other set, then both these sets need to be of the same size. Because you see, we are measuring infinities. If you start counting number of elements kisme zyada hai, you will basically spend all your lifetime to count just one set and you'll never end the counting. The counting will never end because these are infinities. So you cannot compare, you cannot take a scale and measure these. All right, so that is not no longer possible. So therein came this idea that try constructing bijections. Okay. So obviously from the set of from this set to this set, I can construct bijection. The bijection would be f of n is equal to n squared. So this is a bijective relationship. One is attached to 1, 2 is attached to 4, 3 is attached to 9, 4 is attached to 16, and so on. So you can construct a bijective relationship between set of natural numbers and set of n squared. Right. So because there exists this bijection f of n equals to n squared, then we can say that both these sets have the same cardinality. And that is why the word size became controversial, because obviously if set S is completely contained in the set N, then the size of these sets cannot be equal. So that's why we move to a unambiguous word cardinality, wherein we can define it the way we say want it. And then we define cardinality of two sets to be equal if there's a bijection. Okay. So now the idea is, the correct way of saying this is that the set of natural numbers and the set of perfect squares, they have the same number of elements in it. Both these sets have the same size. That is not wrong to say anymore, because cardinality has become a very important thing to compare sizes of infinities. So now we say that the set of natural numbers and the set of perfect squares has the same size or same cardinality. And you can extend this logic to any other set. So let us consider the set 1, 2, 3, 4, and so on, which is basically the set of natural numbers. And another set K, which is basically going to be from 100, 101, 102, and so on. Now, the question is, do these two sets have the same cardinality? And if yes, then can you construct a bijection from one of these sets to the other set? That is the question. So let me ask this question to do you have Ananya. So Ananya,
Yes, sir, we can construct a function like relation like y is equals to x plus 99, and
very
then
good, perfect.
it will be like
Perfect.
cardinal.
Yeah. So perfect, Ananya. So you can construct y equals to 99 plus x. So y of 1 becomes 100, y of 2 becomes 101, y of 3 becomes 102, and so on. So you see, you have constructed a one-to-one onto map from the set of n to set of k. So even though there are 99 numbers which are present in n which are not present in k. Okay, so k, the set k is a perfect subset of n. Even then you have the size of k exactly equal to size of k. So these two things don't necessarily have to contradict each other. They can be true together. Okay, so this entire statement is true. All right. Now let us look at some other sets. The Cartesian product n cross n is counted. So what is the Cartesian product n cross n? It is like an Excel sheet. So if I open Excel for you, okay, so an Excel sheet is basically a Cartesian product of rows and columns, right? So this is basically n cross n. This is the element 1 comma 1. This is the element 1 comma 2. This is the element 1 comma 3. This is the element 1 comma 4, and so on. This is 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 4. So you get the idea, right? 3 comma 1, 3 comma 2, like huh. I wanted a few numbers so that I can give you some examples going forward. Quantities, yeah, it's easier on the eyes. Nice. So this is the n cross n. This is the n cross n matrix, or you can call it the set n cross n. So each of these columns is having the same size as the set of natural numbers. Each of these columns, it goes on till infinity. As you can see, I can press this down button as much as I want, it will go on till infinity. Till some time back, I guess till about a decade back or so, Excel sheets used to be finite in nature, but now they are finite. The algorithm has changed. You can pull them as right as possible, as down as possible. So each of these columns itself is the same size as a natural number. Right? You can construct a one-to-one onto mapping from here to the set of natural numbers also. So let me write down this set 4 comma 1, 5 comma 1, 6 comma 1, 7 comma 1. Okay, so let me just take a snapshot of this. So you can construct a one-to-one onto map. So this entire thing going till infinity here and going till infinity here is my Cartesian product n cross n. Right? N cross n is basically all ordered pairs n1 comma n. Any natural number here, any natural number here. So that is going to be this particular set. Now on this side, if I have just the set of natural numbers, which is 1, 2, 3, 4, 5, 6, and so on, you can construct a one-to-one onto map from here to here. So I'm saying that just this first column itself has the same cardinality as a set of natural numbers. So let me call this as column 1. Let me call this as column 1. This is column 2. Okay, this is column 3, column 4, and so on. So the first column itself has the same cardinality as natural numbers. The set n cross n is basically column 1 union column 2 union column 3 and so on, which is basically I equals to 1 to infinity, the infinite intersection of these columns. So you'll have infinite such columns in the Excel sheet, right? So the n cross n thing is an infinite collection of columns, and each column has the same cardinality as natural numbers. So column 1 has the same cardinality as natural numbers. Column 2 by same logic will also have the same cardinality as natural numbers, and so on. So each column individually has the same cardinality as natural numbers. But the idea does not stop there. The idea is that the union of these columns also has the same cardinality as natural numbers. Now showing one of the columns has the same cardinality as natural numbers is very easy. The more difficult thing is showing a cardinality between n and n cross n. So I want to construct a one-to-one onto map from this set to this set. Now, notice that I can construct a one-to-one onto map between natural numbers and any set if I can basically rank the elements in that particular set. Okay. So when I'm ranking students, let's say in a class, rank 1, rank 2, rank 3, rank 4, I'm basically constructing a mapping from set of natural numbers to the set of students that I have. So any sort of ranking or ordering of elements is construction of a one-to-one map from set of natural numbers to any set. So I want to construct a sort of ranking system here, which becomes a one-to-one onto ranking system. So one such ranking system is that whenever you want to rank a particular element, you look at the 2 digits and you add them. If the digits are ranked, if the sum of digits is smaller, you rank it smaller. Okay, so if I am comparing, let's say 1, 1 and 3, 1, then 1 plus 1 is 2, 3 plus 1 is 4. So 2 is less than 4. So rank of 1, 1 should be less than rank of 3, 1. Okay, because the sum is low. And if the sum is same, so suppose I am comparing 1, 3 and 3, 1. Let's say I'm comparing these two things. So, so when the sum is same, then the one which has a smaller first number gets a higher rank. So rank of 1, 3 is going to be less than rank of 3, 1. Okay. So the one who has the smallest total is ranked first. If total is same, then the one which has a smallest first number gets a smaller rank. So by that logic, this number becomes rank 1. This number becomes rank 2. This is rank 3. Rank 4, 5, 6, 7, 8, 9, 10. And so on it will go. 11, 12, 13th here and 14th here. The 13th rank number is going to be 4, 2. 4, 2 is 13. And this is 14. And I can proceed in this manner. So I have basically constructed a one-to-one onto map. 1 gets mapped with rank 1, 2 gets mapped with rank 2, 3 gets mapped with rank 2, 3 gets mapped with rank 3, 4 gets mapped with rank 4, 5 gets mapped with rank 5, and so on. So in this manner, I have essentially generated a ranking mechanism for all the infinite cells in the Excel sheet. All of these infinite cells can be ranked, and that's why I can say that the set of natural numbers has the same cardinality as the set n plus. Okay. So this idea is very discomforting, unsettling, that an Excel sheet is basically every column in an Excel sheet is a set of natural numbers in itself. And I have, so every column is infinite and I have infinite such columns. Yet the number of elements in an Excel sheet is the same as the number of elements uh, in a natural number. So basically what I'm saying is that set of natural numbers cross natural numbers is also the same size as set of natural numbers. Okay. And this thing is nothing but union of all columns. Now from this and this, what I can say is the set, any column is the same size as the entire Excel sheet, which is basically union of all the columns. So the size of any column of an Excel sheet. Okay, so the size of just this column itself has the same size as the entire Excel sheet. That is the idea. Now, it's a dissettling sort of thing, but our imagination is very restricted to finite things. We cannot imagine things which go on till infinity. So, so that's the idea. Okay, now what okay. So the next proposition is that a non-empty set X is countable if and only if. So, okay, no way. So this example n cross n is countable. So n cross n has the same size in it. This is a very important concept. Okay. And in fact, what I have is n cross n will also be of the same size as n. And all this can be represented in this theorem, which basically says that a countable union of countable sets is countable. Okay, let us look at this particular thing, this Excel sheet example. So column 1 has the same size as the set of natural numbers. What this means is that column 1 of the Excel sheet is countable. And the entire Excel sheet is just union of all such columns. Each column in itself is countable, and you have a union of these columns. So a countable union mean that the union is having the same size as natural numbers. You go from C1, C2, C3 until C infinity. So this is a countable union of countable sets. And a countable union of countable sets is countable. That is the theorem. So this is also countable. Now, what we need to remember from this entire chapter is the word countable, because I have never encountered any question on cardinality as such in past tense, but I have encountered the word countable many times. Okay, so what they'll say is the kind of thing that you can expect in exam is that they'll use the words that consider a countable union of T sets. So you hear the word countable, and suddenly, if you don't know what is countable, you might get like, what is countable? What is countable? Is it finite? Is it infinite? So the idea is it could be either. So countable means sets which are null sets, which are finite, or which have the same cardinality as n. So they are all countable. So what I mean by this particular statement is union Ti from I equals to 1 to, it could be some n or it could be some infinity. It could be n or it could be infinity. Either of these things could be. So the word countable, if you listen to it in the next, if you read the word countable, I don't want you to be shocked. Just think of it as a possibility between a finite union and an infinite. And based on our previous test, which I gave you, and the question number 8 in that test, now you have a working idea of the difference between a finite and an infinite sense. So that is your countable set. Now the question is, are there sets which are uncountable? Are there sets which have a cardinality greater than n? And the answer is that there is. Okay, so our set of n is uncountable. Okay, let me talk about this proposition first. A non-empty set X is countable if and only if there's an onto map F from n to X. Okay, so suppose there's this set n and there's a non-empty set X. So if you can construct an onto map from here to here, onto map means what? Onto map means that none of the elements here need to be unrepresented. There should be no element in X which is not connected with any element in it. It need not be one-to-one. You could have multiple elements in N represented as the same element in X, but there should not be any vacant form. So you can, if you can construct this F which is onto, then obviously what you have is that cardinality of X is less than or equal to cardinality of N. And if you know that it is non-empty, then you know for sure that it is either finite or equal to the size of n. Now again, coming back to the mall of sets, suppose that you go into a mall where there are all the sets lying. Okay, so suppose you go into a mall and you have all these sets which are lying in this mall. Okay, so in this mall of sets, you can basically arrange all sets in their order. Like you see, you go to any mall, you see shirts being arranged in an order, right? So there's this double XS, there XS, then there's S, M, L, XL, double XL, and then all types of XS before it. So clothes are usually arranged in this ordering of their sizes. Similarly, in a mall of sets, you can have sets arranged in orders. The smallest size will be null set, which is size 0. The size larger to that would be a finite set. A size larger to that will be that of natural numbers. Now, what comes after this set of natural numbers? Right? What comes after this is power set of natural numbers. What comes after this is power set of natural numbers. What comes after this is power set of natural numbers. And so on. This thing can keep going till infinity. So the sizes of sets, they keep on increasing one after. Okay. Now, so speaking about sizes, our work mostly comes here. So all such sets are called countable. And everything after this, all these sizes are called uncountable. Okay. So some examples of uncountable sets are here. The set R is uncountable. Set of real numbers is uncountable. In fact, the set of real numbers has the same cardinality as power set of. Now, this proof is generally not required at our level. But I will ask you one last thing for cardinality. Consider the set A, which is set 0 to 1, and the set B, which is the set 0 to 2. Now, obviously, B contains A. Okay, A is a proper subset of obviously. But what can you say about the cardinality of these two sets? What can you say about the cardinality? Can you show that the cardinality of these two sets is zero? Can you construct a one-to-one onto mapping from this set to this set? That is the question.
So B is equals to 2 times A.
Very good. Perfect. Right? So f of A equals to 2A.
So
So A comes from the set capital A and B comes from the set capital B.
excuse me, sir.
Yeah.
So I have a question, like, is it 0 to 1? Matlab, 0 to 2, B is 0 and 2. So is it just 0 and 2 or 0 to 2? Because
No,
there's
this is the square bracket, right? Square bracket. I think I talked about brackets. I don't know. So brackets are important. 1, 2 is just elements 1 and 2. 1, 2 is all elements between 1 and 2, but not 1 and 2. 1
Yes,
and 2 is all elements between 1 and 2, including 1 and 2.
and 0 to 2 is 0, 1 and 2.
0 to 2 is not 0, 1 and 2. It is all elements like 0.5, everything, all the real numbers.
Oh, okay.
All the real numbers. So this is on the real number line, this is 0, 1, and 2. So the set A is basically this set. So everything falling here, under root 2 would be somewhere here. No, under root 1 by root 2 would also be present here. Okay, 1 by root 2 will also be present. So rational, irrationals, everything included. The entire real number line.
Yes, I got it. Thank you so
Okay.
much.
All right. So the importance of brackets. So yeah. So here, if you can construct a function f equals to b equals to 2a, then you have constructed a one-to-one onto mapping from here to here. So what you have is that the set A has the same cardinality as the set. Okay, so set A and B, they have the same cardinality. All right. So now one final thing, consider the set A, which is 0 to 1, and the set B, which is 0 to infinity. Okay, not 0 to infinity. Let's construct 1 to infinity. 0 to 1 open and 1 to infinity. Can you think of, so my claim is that both these sets, they have the same card. I'm like, spoiler alert. Okay, spoiler alert. Okay, maybe this comes as a surprise to you. It came as a surprise to me when I first read it. So I'm making the job easier. The answer is there that A and B have the same cardinality. Can you think of a function which is one-to-one onto from A to B? So give me a function which is one-to-one onto A to B.
So B equals 1 by A.
Very good. B equals to 1 by A. Perfect. Okay. So you see, 0 to 1 is a very small set. Now you can even make this 0 to infinity. That would have been a little more challenging, so didn't give it. But this would be just 1 by A minus 1. Okay. 1 by A minus 1 would give you values from 0 to infinity. So 0 to 1 is a very small line segment, whereas 0 to infinity is the entire thing. Right? But you can construct a one-to-one onto mapping from here to here. In fact, you can construct a one-to-one mapping from here to here. you can just construct it as 1 upon a minus 0.5. I think this would work. Yeah, something like this. I'm not sure. But yeah, you can construct it. So the entire real number line has the same size as any line segment. In fact, any line segment A to B on the real number line has the same cardinality as the entire real number line. Okay. With that idea, I now want to share a video with you about one of this comes from one of my all-time favorite movies. Where to put this in chat? Chat. All right, so you guys can take your time. You can watch it twice or thrice. I'll give you 5 minutes. There are no subtitles sadly, so pay attention to it. So I'll just mute myself for 5 minutes, and you can watch this video, and then we can discuss. All right, so I hope you guys have seen the video. So can anybody explain what Hazel, the character Hazel, is trying to say? And what she means by whatever she's trying to say. There's just a discussion. I mean, there is no right or wrong answer. So whatever you understood by that, it's just a discussion and to build some. Like,
So it's like she said that since there are infinite numbers between 0 and 1 and 1 and 2 and 2 and 3, and if we'll compare the numbers between 0 and 1 and 0 to 2 or 0 to 3, then 1 but we can simply say that those infinities are greater than, we can compare two infinities.
okay, all right, fine. So, any other understanding from this? Anybody else who wants to pitch in? Okay, so the idea is, the premise of this movie is that both these lovers, they are fighting some terminal diseases. So their love story is pretty short. So what she's saying is that like 0 to 1 has infinite numbers. And 0 to 2 also has infinite numbers. Now it might seem that 0 to 2 is a larger set. So if you had a love story which lasted for, let's say, 60 years, somebody would feel that because 0 to 60 is a larger set, this love story is longer. But what she's trying to say here is that even if your love story, their love story is not too long, it's a very short one, but still it is an infinity, and that this infinity is no less than any other infinity. That is what she is trying to what she means by thanks for our little infinity. So the little infinity here is the short time that they have, and what she's trying to say that even though they had this very short time, their love in no sense is smaller than any lengthier love story. So so that would obviously, when she says that this 0 to 1 is a smaller infinity than 0 to 2, there's a lot of mathematicians who go berserk over. She's saying that, suggesting that 0 to 1 is smaller than 0 to 2, when it is not. It is actually of the same size as 0 to 2, which we just saw. Okay, we just constructed an interval from here to here. So we just saw that these two infinities are actually the same size. So when she's saying that it's a smaller infinity, what she means is the idea that 0 to 1 in a length format, 0 to 1 seems smaller. But when you talk about the exact size, they are not different. They are the same size. Okay, so that's about cardinality. I will give you there's no problem set on cardinality. There's a direct test which I'll be sharing with you. So I'll share that test with you. By the way, how many of you have given this test? 4 of you have given this test, which is not cool. You guys should be giving tests. I take a lot of time making these tests. I don't like, most of these questions are made by me. I try to make them at a level which give you the best revision possible, but they are going to be the most efficient if you appear for them in the stipulated time, like when I assign it to you. Otherwise, they won't be as beneficial. Okay, so let's start the uh, new topic, sequences in series. Okay, the homework is obviously the entire past years of set things. So that is your homework. I don't think I'll be able to assign any homework from this one. And yeah, doubts I'll be taking up on a weekday lecture, because I think I need to have some amount of. I'll take doubts on one of these weekdays. Most probably I'll take it on Tuesday or Wednesday. So we'll take a doubt session there for the doubts from the problems. Okay. sequence and series. Okay. So before sequence and series, I just want to delve into this triangular inequality, which is an important thing. You could be asked the proof of this inequality in the ISS objective part, so you need to remember this proof. So the triangular inequality states that mod of x plus y is always less than equals to mod x plus mod y. Okay, so this is easier to see, right? So if x and y are both positive, then mod of x plus y will be equal to x plus y, and mod x plus mod y will also be equal to x plus y. So they are both. But if x is positive and y is negative, such that let's say x is let's say larger in magnitude, and mod x is greater than mod y, for sake of argument, then what we get is mod of x plus y, right? Mod of x plus y. Now x is positive and y is negative. So, and mod x is greater than mod y. So mod of x plus y will actually be equal to x plus y, where y is negative, right? So remember y is negative. So x plus y, so x is let's say plus 4 and y is let's say minus 3. Okay, plus 4 and minus 3. So mod of x plus y is 4 minus 3, which is basically. Whereas mod x plus mod y in this case will be equal to x minus y, which basically becomes 4 minus minus 3. So that is equals to 7. So when they are of opposite signs, x and y are opposite signs, then then these two numbers are unequal. But when they are of the same sign, then these two things will turn out to be. All right. So when they are of different signs, then this thing becomes larger. When they are of same sign, then these two things become equal. So that is the gist of it. Now, obviously, how to prove it? So an easier proof is this one line proof. Now, obviously, you can take different cases and you can prove it that x greater than y. Sorry, x and y both positive, both negative, and you can make different cases and prove it. That would be a lengthier proof. But if you can't think of anything, make cases and prove it like I just did here. So you'll have 4 different cases: x greater than y, x less than y here, and mod x greater than mod x less than mod y here. So we have 4 different cases. If you can't think of anything else, just make cases and prove it. You'll get full marks. It will be lengthy. It will be a little frustrating, but it won't be wrong. A simpler proof comes from this thing. So you take the right hand side. Let me just remove all this stuff. Okay, you take the right hand side and you square it. So mod of x plus mod of y whole square. So this is mod x square plus twice mod x mod y plus mod y square. Expansion of a plus b whole square. So mod of x ka whole square is nothing but x square. Mod of y ka whole square is nothing but y square. And this is twice mod x mod y. Now, twice mod x mod y has to be greater than or equals to twice xy. Okay. This comes from the simple fact that mod x mod y has to be greater than x into y, because x into y can be positive or negative, but this thing will always be positive. Right? Magnitude wise, these two entities are going to be the same, but the sign of this thing will always be positive, whereas for the right hand side it could be negative. All right. So since this thing is true, you can just add x square plus y square on both sides, and the inequality will remain. So what you get is this inequality now. What you get is this inequality now. And finally, the right hand side here is x mod of x plus y whole square. This is basically x plus y whole square, which can be written as mod of x plus y. Now the final deal here is this square is greater than or equal to this square. So the last thing is mod x plus mod y whole square is greater than or equals to mod x plus y whole square. Now, since both these entities have been constructed as positive things, you can remove the root without changing the sign of inequality. All right. In general, saying that if y1 square is, sorry, if a square is greater than b square, it does not necessarily imply that a is greater than b. Right? This is not true because a could be negative, a and b could be negative. All right, so a greater than b does not imply these things. But since this thing is summation of mods, so this is positive and this thing is also positive because it is x plus y mod. So since this thing happens, I can remove the squares. All right, so when you're doing such things, be mindful of the possibility of having negatives because that could spoil your proofs. So now that you have this, you have essentially proven the triangular inequality. Now the next proposition is if x comma y belongs to real numbers and mod of x minus so mod of mod x minus mod y is less than equals to mod of x minus. Now again, if you can't think of any proof, so ideally this proof, this proposition is an outcome of triangular inequality. Now they might not ask you triangular inequality directly. They can ask you some outcome of triangular inequality like this. So it's not that they ask it a lot, but they can ask it. And if they ask it, sometimes you might not be able to do this. But the thing about subjective paper is that you have 2 hours for 4 questions. You get half an hour for 1 question. So you have a lot of time on your hands. So you can basically construct and take all possible cases. There are only 4 cases here. X and y both positive, x and y of different magnitude, mod x greater than y, mod x less than mod y. So you can construct different cases and do something even if you can't think of anything. Just write something. Don't write bullshit. You don't write like crap. Okay. Write meaningful things, construct it into cases, let it be a longer proof rather than being no proof. That would be my solution. So how do I show this thing using triangular inequality? Now using triangular inequality, mod x can be written as mod of x minus y plus y. Now what is triangular inequality? This is my triangle. Mod of x plus y is less than equals to mod x plus y. So I can break this down into 2 things, x minus y and y. I can call this as a and b. So from triangular inequality, I know that mod of a plus b is less than equals to mod a plus mod b. Okay, now mod a here would be mod of x minus y and mod b here would be just mod of y. So what I get is mod of x is less than or equal to mod of x minus y plus mod of y. So I can take this on this side. What I get is mod x minus mod y is less than or equal to mod of x minus y. So you can call this as inequality. Right. In the next part, what you can write is you can do the same thing. You can start with y. You can write that mod of y is equals to mod of y minus x plus y. Sorry, y minus x plus x, which is less than or equals to mod of y minus x plus mod of x. And then you can take this on the other side, you get mod y minus mod x is less than equals to mod of y minus x. And you can call this as equation inequality. Now notice the right hand sides of both these inequalities are same. The right hand sides are same. The left hand sides, they both need to be less than this. So what I get in the end is that mod x minus y should also be less than or equal to, no, sorry, mod x minus mod y should also be less than equals to mod of x minus y, and mod y minus mod x should also be less than equals to mod of x minus y. Now, both these things, if they are true simultaneously, they can be written in a single argument that modulus of mod x minus mod y should be less than or equals to mod of x minus y. Right? So this step is important. So this is basically, you can think of mod x as the number a and mod y as number b. So what I'm saying that is mod is that a minus b is less than something k, and b minus a is also less than something k. So these two inequalities can directly be written as mod of a minus b is less than this thing. Because one of these things is going to be positive, the other thing is going to be negative. If not both zero, if a and b, if a is not equals to b, then one of these things is positive, other thing is negative. So if that is true, then this thing gives me the max of a minus b and b minus. So I'm saying if both these things are less than k, the max of these two things is also less than k, and max of these two things is nothing but mod of a. So the max of these two things is nothing but modulus of a. Okay, so that's about triangular inequality. Don't spend much time here. I have never seen any question from triangular inequality, but I don't really know. So I like to teach it just to be sure. Plus, it comes handy in some proofs. So that's why it's here. Now, sequences. So, what is a sequence? A sequence is generally a sequence of real numbers is a function defined on the set N2. So till now we have heard of sequences as a sequence of numbers arranged in some order. Here we are defining it as a function. It's a function defined on the set N going to the set I. What this means is that if you have this set of natural numbers N and another set of real numbers R, 1, 2, 3, 4, 5, 6, and so on. A sequence is just numbers. This is real number R1, this is real number R2, this is real number R3, this is real number R4, this is real number R5, R6, and so on. So it's a function defined from the set of natural numbers to the set of real numbers. Now it's a very complicated way of saying the same thing, that a sequence is just an arrangement of numbers. But what we are saying here in a very subtle manner is that this ordering of the numbers is important. So the sequence 0, 1, 0, 1, 0, 1, and so on is also a sequence. And another sequence 1, 0, 1, 0, 1, 0 is also a sequence. Let me call this as sequence 1 and let me call this as sequence 2. So even though the numbers appearing in these two sequences are same, because the order of the numbers is different, these two sequences are different. In fact, we can go one step forward and you can say that, let's say sequence 2 is 1, 1, 0, 1, 0, 1, and after this it is all same. So the only difference which is occurring is in the first character. So the first element is the only one which is different. And even in this case, the two sequences are different. So what we are saying is that the order in which the numbers appear is important. And another thing we are saying is that it should be a function defined on the set of natural numbers to set of R. So natural numbers go on till infinity. So this sequence cannot stop at some point. It cannot be like final number 100. It cannot stop. It has to go on. because the set of natural number goes on till infinity. All right, so we have learned two important things for any arrangement of numbers to be sequence. One is that the ordering matters. Numbers can repeat again and again. That is not a problem, right? So you can have just two numbers, 0 and 1, which keep appearing again and again. That is perfectly reasonable. So 1 gets mapped with 0, 2 gets mapped with 1, 3 gets mapped with 0, 1, 0, 1. That is fine. It is still a function. What cannot happen is that it runs out of terms after some time. This cannot happen. Okay, that is not possible. And ordering matters. You cannot change the order and call it the same sequence. If you change the order, it becomes a new sequence. So that's all you need to know about sequence. It is going on till infinity. Or it has to go on till infinity. Okay. Now, sometimes you can write sequences as a formula. Sometimes you can't. Okay, so we are going to call sequences as xn. Xn is going to be the generic name we represent. So it's just an ordered list of numbers. Now, consider the sequence x, which is 1 by 2, 1 by 4, 1 by 6. And so on. So you can call this sequence as 1 by 2n. Right? So you keep changing n for different natural numbers. You keep getting different elements. So n is 1, 2, 3, 4. So for 1, you get 1 by 2. For 2, you get 1 by 4. For 3, you get 1 by 6. For 4, you get 1 by 8, and so on. So sometimes you can write it in a formula. Sometimes you might not be able to write it in a formula. For example, the temperature of Delhi today, at any point on any day, the average temperature of Delhi on any day. So this is a infinite sequence. It will go until infinity, assuming Earth stays on till infinity, which won't, but for all practical purposes, it will, or at least till we will exist if Earth exists. So by that logic, it's a sequence, and it does not have a formula. Okay, it's not like we can predict exactly. So it varies. It is possible that a temperature today is the same number as the temperature tomorrow, but that is a infinite sequence. Now, why are we studying sequences? Because a lot of things in economics are sequences. For example, inflation. So the inflation rate is essentially a sequence. So you look at a sequence and you try to understand where is this sequence headed? What is going to be the inflation after 1 year or 2 years? Or how it's going to affect what is employment? Look at numbers. We are in general people who like to draw trends. We look at share market and we try to figure out kahan jayega. We look at employment. This is the start of our data analysis thing sequences. So we look at some numbers and then we try to predict where is this going? Okay. So then we have this Fibonacci sequence. So Fibonacci sequence is a very important sequence in the physical world. So why is Fibonacci sequence important? Because the numbers of this sequence, they keep appearing in multiple things in real life. I'll share a YouTube video with you all on the importance of Fibonacci sequence because we don't have the time. I ideally show it in class, but since we don't have time, I'll just share it with you. So the sequence is defined as you define first term and second term, and then all the subsequent terms are the sum of the previous two terms. So first term is 1, second term is 1. So the third sum will be 1 plus 1, so that is 2. The third term will be 1 plus 2, so that is 3. Then 2 plus 3, so that is 5. Then 5 plus 3, so that is 8. Then 8 plus 5, so that is 13. And so that is your Fibonacci sequence. So like I told you, the important thing is for us to sometimes figure out what happens to a sequence as it keeps progressing. Is it going to some point? So let's say we see the inflation numbers for this year. Okay, and we see that the numbers look like this. So it was, suppose we are looking at price of oil. Okay, we are looking at price of oil. So we all see that price of oil is increasing right now. So we saw that when RBI changed the policy, suppose, let's say the government changed the policy on some days. On this day, the price of some particular type of fuel was 120 bucks. Okay, then we see that as days progress, this price became 125, 135, 145, 149, 153, 152, 150, sorry, 153, 154, 155, 155.5, 156. Suppose this is weekly data on week 1 rather than weekly data, week 0, 1, 2, 3, 4, 5, so 156, 156.5, 156.9, and so on. So the idea is that yes, it increased very fast initially. Then it kept on increasing later on, but it is increasing at a smaller pace. So if this is where we are right now at 156.9, the prediction is that unless something changes in the economic structure of production or demand or supply of oil or the import duties or anything, it is predicted to hover around 160. Okay. So how did we come at this argument that it is going to hover around 160? So what we are saying is that the limit of price of oil sequence, the sequence of price of oil seems to be something around 160. So this is the prediction that we are making just by looking at these numbers. So now, right now we don't have much technical details about what is limit of a sequence and all that stuff. So, but in the next class, we are going to look at exactly that. We are going to look at limits of a sequence and how to find limits. What is the meaning of limits, first of all, and then how to find it and all this stuff. Okay, so that's going to be our topic on sequences. Okay. Sequences, again, a pretty important topic. So it has appeared multiple times, sequence and series. The series is also included in this chapter. Yeah, sequence and series. So we'll do both these. So it's going to take about 2 lectures, I think, this topic, which is rather long. So yeah, so I can only give the next problem set after that. So for now, your homework is just doing the past years of set theory. I'll share the solutions with you all, and we can discuss them sometime next week. We can start with the discussion first. It's not going to end in one sitting, so we might have to do multiple sittings for that. But I like to have doubt sessions on weekdays because then we can go at a faster pace. And then people who don't have doubts don't have to attend, so I'm not wasting everyone's time. So I'll share the solutions with you all for the years, past years that I've made solutions for, and you can cross check with those, and then if you have any further doubts, you can raise it on the doubt section. Also, tomorrow is the micro lecture. So for the micro lecture, I have given a problem test. So please attempt it before 4 o'clock tomorrow, so we can discuss it tomorrow. And I don't think I gave any problems set for that. I gave the test bank questions for that. So I already told you that the test bank questions, the solutions which we discussed yesterday, I've uploaded them. So I will take doubts apart from those questions. So let's say question number 13, 15 are discussed. You have question number 14 as a doubt that is not given in the solutions. So I'll discuss those, and if after looking at solution you have a doubt in any solution, then obviously we can discuss. All right, so let's stop at this today. Start working with the fastest. Okay. Fine. So I'll just end the class. I'll see you guys tomorrow, same time. Do attend the next. Okay. All right. Ending the class. Bye, guys.
Thank you so
Welcome.